jump right in here. So it says, drawing 3 aces in a row from a standard deck of cards when the drawn card is returned to the deck. Okay, and you're just trying to decide whether it is independent or dependent, is that right?
And I have to do the probability of drawing the 3 aces.
Yeah, but for part A, it's just independent or dependent. Okay, so the idea is that there are 4 aces in a deck of card out of 52 cards. Okay, so the probability of an ace, probability of drawing an ace, is 4 out of 52, or 1 out of 13. Okay, now if you return the card to the deck, okay, you have not changed the number of aces or the number of cards. So the next time you do this exercise, when you, like, imagine you have a deck of cards and 4 aces, and you grab an ace and you put it back in, you still have 4 aces and you still have 52 cards. Okay, so notice that the probability does not change.
Okay.
So these are independent because the probability does not change between the events. You know, you can think of this as event number 1 and event number 2, and event number 3 is exactly the same.
Okay.
All right, so now we can answer question B, letter B. So letter B here. Do you want me to check your work, or do you want me to?
If you can, I think I got most of it right. I'm just not really sure.
Okay, so the difference in part B is it says no card replacement. That's very important. So the first ace, and so what you assume when you're doing these is that it's success each time. And so that means the first card is an ace. Okay, so the first card being an ace means there's 4 out of 52, and you've successfully drawn an ace. Okay.
Okay.
So that's ace number 1. Ace number 2, there are now 3 aces because you assume you've already drawn one. And since you've already drawn one, the number of cards goes down to 51.
Okay.
Ace number 3, you have 2 aces left because you've already taken out 2, and there are only 50 cards left.
Right.
So you can think of it as the probability of drawing an ace and an ace and an ace. And in general, not always true, but in general, and means to multiply.
Okay.
So this is this result here is what they're looking for part B. Do you know if they want it as a decimal or as a fraction?
My teacher said fraction, decimals, or percentages. He'll accept any of them.
Okay.
As long as it's a simplified fraction, though.
Yeah. Yeah. So this one, I mean, there's a lot of ways to do it. Put in the calculator. Let me get mine out here to be able to give that to you. It wasn't quite set up with that. All right. So I like simplified fractions as a first preference, but if you don't, that's okay too. I'll give you both numbers. So this is actually, this one does not. No, it does become a nice fraction. This is 1 out of 5,525.
Okay.
Is that what you wrote?
Yes, it is.
Okay, because the work looked very different than what we did here, but that's okay. As long as you get the right answer, that's really all that matters. Especially when you get to college and you're just trying to get through classes. Unless you're going into math or some sort of engineering field, then maybe we give you a little more discussion on this.
Right.
All right, can we move on to letter C, or do you want us to go on to D?
D.
D, okay. All right. So D is dealt 5 black cards off the top of a deck. So if you haven't gone out to Wikipedia or the internet to find what a deck of cards looks like, I would recommend doing that so you're familiar with all the things that might be in a deck of cards. So there are 26 black and 26 red cards in a deck. So you assume 5 successful events. So the first black card is 26 out of 52. And then because you've drawn one, there's only 25 black cards left out of 51, times 24 black cards left out of 50, and so on.
Okay.
All right, and this one most likely going to be a decimal. It's pretty low. And if you're into like poker, this is called a flush, and it's not as likely as some people would make you think to believe. But
Over Christmas, my mom had us try to play gin.
oh,
That
cool.
was interesting.
Yeah.
We've never played it before.
Yeah, the card games are fun. They're a great way to pass the time, especially before we had phones and TVs and all that stuff. But this is actually 0.0253, and I'm just arbitrarily going out to 4 decimal places. If you need to go out more, you can do the calculation. But this is 2.5%. That's pretty low. That doesn't happen very regularly.
Okay. And this would be dependent or independent?
Oh, these are dependent. Sorry, and the last one is also dependent.
Okay.
They're dependent because the next one depends on the first one, because you have to assume that you made an ace. Here you have to assume that you took a black card. So this is also dependent.
Okay.
All right, can we go into letter F now?
Yes, please.
Okay. Discovering your 3 best friends all have birthdays in April. Okay, so there's a little bit of a few assumptions that I have to make here. This problem should be written slightly differently. The idea is that you have a 1 in 12 chance of, like, your birthday month is 1 out of 12.
Okay, I get it.
And you have to know that in advance. I don't want to get too crazy on this first lesson doing this, but like, for example, not every month is the same number of days. Birthdays are not uniformly distributed among the months. I think there's some that are more popular than others. It's things like that. But it's kind of like the previous problem. It's like, all right, friend 1, 1 out of 12. This is friend 1. Friend 2 is also 1 out of 12. And then friend 3 is also 1 out of 12.
Okay.
Now these are independent because the probabilities are the same, but you can also look at it from the perspective of, like, your birthday and my birthday are not in any way related. And same with maybe a friend you've got elsewhere. Like, they're just not, like, one does not impact the other.
Right.
All right. So that is like, I would probably go fraction here on this one. This is 1 over 1,728. And that's pretty small. These are independent.
Okay, that makes sense.
Interesting. Letter G is really similar. Randomly meeting 3 internationals in a students who are on campus with a 1 in 12 chance. Okay, 1 in 12.
See, I wasn't really sure what to do with the 1 in 12. Wasn't really.
Yeah, I mean, I'm tempted to say it's 1/12, but it could alternatively, like, if this were I'm trying to think of what this is, not a ratio. Maybe that's a ratio. Anyway, then it would be 1 to 13.
Okay.
1 over 13, because the bottom number is the sum of the 2 numbers. Do you have the ability to ask your instructor about this one? Can you send off an email that says, does this mean the probability is 1 out of 12 or 1 out of 13? And the only thing it changes is it's 1 out of 12 times 1 out of 12 times 1 out of 12, or it's 1 out of 13 times 1 out of 13 times 1 out of 13. And I don't know which direction to tell you, because the previous problem, pretty sure, is 1 out of 12. And it's weird that there'd be 2 problems in a row with exactly the same answer.
Okay.
So
Yeah,
I guess if, like, you needed an answer today, I would tell you to go with this one.
Okay.
But I mean, it's one question, one part of one question.
Yeah, I mean, I learned that my teacher grades, my math teacher math teachers, they can grade all different ways. This
Yes.
one, if you show all your work and if it's wrong, you get docked points, but you can still get some points.
Good. Good. So we want to go for that here.
Yeah.
And that's the kind of thing that that's the kind of thing you will use on the tests as well. Show your work. Okay, we moving on to 3C.
3, yeah, C.
Okay. There's no space to answer it. That's
I know, it's weird. I just printed off like the worksheet, and then C has no space, whereas all the other ones have plenty of space.
so this is a great problem where if you had that deck of cards image, you could just count the ones that match this criteria. So let me do that here first, but also show you a second way.
Okay.
Some teachers even include this on like the first page of the test. Okay, so you're looking at cards 2 through 10. So you can either count them or put check marks or something, but you're looking at 2 through 10. So basically all of these
Okay.
in this grouping, and you could check, but that takes a while. And then or a diamond. So there's another diamond, another diamond, another diamond, number diamond, like that. So you could literally count. Now there's 52 total. So sometimes it's better to count the ones that are excluded because you're counting less. So what I mean by that is you're excluding these and then this grouping here. So you're excluding 3 plus 9 or 12. So it's the other one is 40 out of 52, and then you would simplify that fraction. 20 out of 26, 10 out of 13, like that. There's alternatively, and it's kind of the same, but it's if you don't have the picture. Let me know when I can show you that, or you.
Oh, there was no space. I had to flip around real quick and write it down. Okay, yeah, you're good.
All right. So the other way is to like, okay, it's like, how many 2s are there? There's 4. How many 3s are there? There's 4. How many 4s are there? And you're doing the same thing just without the picture. Now, where it gets harder is, okay, well, there's also diamonds. There's diamonds, ace through king, which is 13 total, but you've already dealt with one of each of these. So it's like, well, how many, it's like also, okay, there's also an ace, a jack, a queen, and a king. So there's another 4. So it's 4, 8, 12, 16, 20, 24, 28, 32, 36, 40. I think the picture is better, but if you don't have access to that, it's harder to do that, use that approach. But this one relies on you knowing like what's in each suit and just counting,
right?
Kind of that way. All right, letter D, 3D here.
Okay. Oh, and so this would be overlapping, right? Sorry.
Yes. So I didn't really understand that. It's determine whether are overlapping or non-overlapping. Yes, this one is overlapping, and the reason is because there are some that are both. Are both. There's a diamond. A 2 is both a 2 or and it's a diamond. And this will make it more clear when I do this. So here's the picture again. Okay, here are all the diamonds. Okay, and like here are all the 2s. Do you see how there's an overlap right there?
Yes.
That's what is meant by overlap, where they're both true. Both true. All right, so next question here. All right, randomly meeting either a woman or a Republican in a group of 10 Democratic men, 10 Republican men, 30 Democratic women. Are you just supposed to say whether? Oh, and you find the probability. Okay.
Probability and whether it's overlapping or not.
All right. So my question to you is there a woman who is a Republican in this description?
Yeah, there's 40 of them.
Okay, so then it's there. So you know right away that there's overlap.
Okay.
All right. So the other way to do this when you can't like you don't have a picture or you can't do that. Sorry about that. So probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. Did you see that in class or in your notes somewhere?
Yeah.
So so in this problem, you can think of it as Republican, or sorry, woman first. W for woman, Republican. So that would be W, Republican, W, Republican. So we're looking for the probability of a woman plus the probability of the Republican minus the probability of the woman and Republican. So you have to make the assumption here that there's 10 plus 20 plus 30 plus 40 people. That's your total.
Okay.
That's 100. So there are, well, we want the ones that are women. So we're interested in the Democrat women and Republican women. So there's 70. 30 plus 40 gets you to 70. Republican, there are 20 Republican men and 40 Republican women. So we go 20 plus 40. I'm showing the numbers just in case you want to look back and know why those are the right numbers. And then woman and Republican is the 40. So you got 70 over 100 plus 60 over 100 minus 40 over 100, which equals 90 over 100 or 0.9, 9/10.
Okay. I caught up.
Okay, and this one's definitely overlapping, but I think we already covered that.
Yes.
All right, so let's do letter E.
Letter E, I was super confused how to do this one.
Okay. Yeah, you're on the right track by saying that it is non-overlapping. So 3-child family. So here's this is a variation on like a coin flip problem.
Okay.
So I'm a male, so I'm gonna be, well, they use girl, so we'll use boy and girl on this. So B is the first possibility, 3 boys. Okay.
Right.
Boy, girl. Now notice when I'm making this list that I'm only changing one thing at a time.
Right. That makes sense.
Okay. And like the next one here, I'm going to go boy, girl, boy. Now it might feel like I've changed 2 things, but you could go girl, girl. This is just the way that I process this.
Okay.
Girl, girl. All right. And then girl, boy, boy, girl, boy, girl, 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 boy, girl, girl, girl. So there are 8. And like I said, if you look up a heads tails table, it's very similar to this. Okay, so the probability, well, there's 8 total. There's 8 possibilities in a 3-child family. So we got to count the ones that are 1 or 2 girl. 1 or 2 girl. So let me highlight those here. So there's 1 girl, 1 girl, 2 girl, 1 girl, 2 girl, 2 girl. Then you just count. You count the ones that are there, 6. That's 3 out of 4.
Okay. That makes sense.
So if you're studying a test, it would be, the other problem would be like randomly selecting out of 3 coins, 1 head or 2 head, or 1 tail or 2 tails. It would be the exact same style of problem.
Okay.
What is number, oh, 4, at least once rule. Okay, sorry, using the at least once rule. Got it. All right, so we need to do letter B for B.
Yeah.
Okay. I do like the way this is organized because this is it's very confusing to do a bunch of different types of problems. Uh, they're trying to organize all of them together.
Yeah, my teacher did a decent job. He had videos per which one. So like the once rule or whatever, he would go through 2 to 4 examples on that through the video. And I was able to get, that's how I was able to get some of them because the questions were very similar. And then some of them I'm like, I feel like you're throwing things at me and I don't know how to couch them.
Yeah, there's a lot of like life experience stuff that you don't have yet with this class. Like I mentioned with the deck of cards, maybe rolling dice. If you have the time, I would encourage you to like get a deck of cards out or watch some videos on cards and dice, not for the purposes of gambling, but for the purposes of like figuring out these things that so you're more comfortable with them. All right, so now this B, it's like the at least one rule. So when you say the probability of at least one, and this was probably covered in your class, it is 1 minus the probability of none.
Yeah.
So we actually want to find the probability of no aces. Okay, and maybe that's hard or confusing because like, what do you mean by no aces? A couple of ways to do that. Like when I look at a deck of cards, I know that there are 4 aces in the deck of cards. So there are 48 non-aces. But you can alternatively do this as the probability of aces and subtract it from 1. So there are 4 aces in a deck of cards, and if you subtract it from 1, it becomes 48 out of 52, which is exactly the same. So either way, I guess I'm trying to show you 2 ways to come up with this first part of the answer. Okay.
Yeah.
Now, this is only kind of like a little small starter part of the problem because you're actually doing this 10 times. So each time you draw, it's like multiplying by the same thing because you're replacing the card.
Okay.
Okay. And I could write this out 10 times, or like I think I saw in one of your problems, you can raise it to the power of 10. But this right here, this part, this thing right here is the probability of none. So we still have to make that final step of subtracting that result from 1. If anything I'm saying here is unclear, please interrupt me. Please ask questions. I feel like I'm going faster than we normally go through math problems. So
a little bit, but I think it's probably because I have a little bit of a basis on this and I actually understand it better than other things. But yeah, no, I get it because you're replacing it. It's going to say 52 instead of going down. I believe, right?
Yes. So if it were replacement, well, so the thing is, there's only 4 aces, so you could never get 10 times. That would be like 4 times, and then it would
That's true.
but it could go down. Yeah, and so what you're thinking about is a lot of these, is it like replacement or no replacement? Overlapping, no overlapping. Yes, all of these things come into play when you're doing this.
Okay. Yeah, no, that makes sense.
All right, another small point I'll make here is like this answer feels super reasonable. It's all probabilities are from 0 to 1. In your class, because it's a class, it's not real life, you should expect to get numbers that are not like you would not expect to get like an answer like this very often in your class.
Yeah.
Similarly, you would not expect to get, this very often in your class either. They're kind of in the space. So if you get an answer that seems unreasonable, recheck your calculation. Okay, that's for B. What's the next one here? 5.
So it's all the way to page 5,
Okay.
pretty much. And it's the below, not the multiple choice, the one below it. Like consider the following paradox.
Family in Longview has 2 children. That
Yeah.
one.
Yeah.
Okay.
This one, there's 2 possibilities and I don't get which one would be correct. The 2 ways to do it.
It's interesting. Is the teacher from Colorado, Longview?
Actually, it's Longview, Washington.
Oh,
That's where the
Washington. Okay.
college is.
Oh, that's right. You're doing that there.
Mhm.
One of the children is a boy. What is the probability that the other child is a boy? Okay. Um, so here's what we don't know, and I can come at this because I actually have not read the rest of this. We
Okay.
don't know, we don't know the order. We don't know whether the first child is a boy or the second child is a boy. I'm sorry,
Right.
we don't know if the boy is the first or the second.
Mhm.
Um, we know what the space is for boy and girl because we've looked at that before. We know that it
Mhm.
could be boy boy, boy girl, girl boy, girl girl. Um, the other thing I guess that could be relevant here is that what was I going to say? The there are they independent events? Like, is the probability that they had a boy mean that they're more likely to have another boy, or they had a girl, probably that don't have another girl? So those are some things that I'm thinking of.
Mhm.
Um, we also statistically, that's where part A comes in here. So like, if you look at the populations, well, sorry, if we consider that there's only one gender of one child, so that's the whole stuff you see in the world around us today, but they're saying there's only one gender or two genders, boy and girl. They're equally likely. They're saying like, hey, it's either boy or girl, 50%. If we look at
Mhm.
actual population totals, there are more women than men. Men die earlier in life because of the dumb things that they do in general, wars, stuff like that. So keep that in mind as well. Uh, Here we go. Let's look at the next one
Or
here.
like in my year when I was born, I had a lot of boys around me. So like all my friends were boys and whatever.
Yes,
There was
right.
not a lot of girls. And then with my brother, he was born in 2008. All of his like he was like out of three boys in a 28 classroom, and all the rest were girls.
Yes,
So it's
yes.
like it just happens.
Yeah, that was kind of the birthday month. I mean, sometimes you just see more in one month versus another. Um, okay, so it says, given a two-child family with at least one boy, here are the possible combinations: boy and girl, BG, GB, BB. Okay, there are three possibilities, and only one is both boys. The probability of the second child being a boy is 1 out of 3, or 1/3. Okay,
Mhm.
so they're looking at this from the perspective of um, of that the because you know that there isn't girl girl,
Mhm.
they're looking at it from the perspective of you already know the fact that there's a boy. Like that's an inherent assumption of the problem, is that, hey, you have a boy already.
Right.
Like they're saying, because this is true, okay,
Mhm.
like we know that there's not a girl girl, so we can exclude that from the sample space. You're excluding GG from the sample space.
Okay.
Now we're going to get to, I think we're hopefully we can um okay, so sorry, so now the first one, the reason that the first one looks at it as in the following way: it looks at it as boy boy, boy girl, girl boy, girl girl. And
Okay.
this first one looks at it from the perspective of, we don't know what the um we don't know what the two children are. We just know that if they have two children, these are the possible outcomes.
Okay. I get that.
Okay, so they're saying like it, like, and I think of it as, well, if you didn't know the answer, you didn't know the answer about one of the children, then
Mhm.
A would be, uh, but it's also, they're also only talking about one child,
Right.
which is interesting because it's if it's one child at a time, yeah, every time it's 50%. So I'm gonna have a hard time answering this question. I'm gonna draw an analogy to, have you ever heard of Let's Make a Deal, the show?
Yes.
Okay, so at the end of the show, there are three doors: door number one, door number two, and door number three. All right. So
Mhm.
there is the grand prize is behind one of the doors. All right. And the grand prize is whatever, a car, used to be a car back in the day. And you have a 1 in 3 shot of winning. So like you would pick, I'm sorry, I would pick door one. I'm like, yeah, it's door one. So then the contestant or the host would say, okay, Emma, door one's out. Door one is out. And there's a prize behind, there's still prizes, but they said, do you want door number 2 or door number 3? Now you are only choosing between those 2 doors now. So
Right.
if the prize is behind door number 2 or door number 3, you have a 1 out of 2 chance of winning, but you don't know that. All you know is that you can't choose number 1.
Right.
Okay, so the answer to this question. Oh, and by the way, it's better to be the contestant number 2 because you have a higher probability of choosing. So, but as a side, you have to decide to answer this question. Because I don't think there's a wrong answer here. I think it's like you have to decide whether, like we said down here, whether the fact that you already know the gender of one child means that you exclude the possibility that there's 2 girls.
Right.
So it is 1 out of 3 here. I tend to lean towards B if you were asking for an answer, because if we know there's 1 boy, then the possibilities are BG, GB, BB. Or if you're looking at it from the standpoint of what is the probability of a boy at birth, then you would choose letter A. So it's like letter A is like when you're born, you're either boy or girl, 50%, 50%, closed, end of story. For B, it's more like, well, since you have some information, basically like some dependence versus independence here.
I get that. Okay.
And I don't think you can go wrong. I think that you can just explain as briefly as possible.
Yeah, makes sense. Still have time.
Yes.
That was
Some
the
other
last.
stuff we can look at, or
I was wondering if we could actually go over and see. There's a few questions that I'm a little bit questioning on.
okay.
I was wondering if we could check them.
Of course. Which where do you want us to start?
On. Sorry. Please. Three A on page 2. One. I think I did that right. Because I did a lot less work on this one than I usually do, so I'm worried.
Yeah, so let me snip that one in, and
Yeah.
I'll probably grab that picture again because I think it's really helpful to see the deck of cards here. So it's a queen or a club. So what I was trying to allude to earlier is when there's overlap, what you don't do is you do not double count.
Okay.
So you only count 1 time. So if we look at okay, club, heart, no, spade. This is the club.
Okay.
I think.
No, that's a spade, isn't it?
No, it's a spade.
Okay.
This is the club. Is that right?
Yeah, I think so. Although
Okay,
I call it a clover.
yeah, diamond, heart, club,
Spade.
spade, club. Okay. I don't play cards, and I don't. This world is a little foreign to me because I don't. It's a bad world to be in. Or queen, right?
Yeah.
So if you miscount, right? If you're like, oh, it's 4 plus 13, that's wrong because you have to subtract out the one that you're double counting. So don't do that. Always only count the one that you so like I look at it as 13 plus 3, which is it's the same, but it's 16 out of 52, or 4 out of 13, I think.
Okay.
Is that what you have?
I have 4 out of 13, but I don't think I did that to get to it. I did.
Well, you did the 4 out, you use the fact that it's the probability of one plus the probability of the other minus the probability of both.
Okay.
And that's correct. Like there's multiple ways to it. I'm more of a counter, especially if I know the sample space. But as you saw in that Republican and Democrat and male and female problem, you sometimes have to use this formula to figure that out.
Yeah, that makes sense. The one, okay, so there's page 3, after 4, letter A. This one, my teacher did one so similar to it. So instead of getting at least 3 in the 4 rolls of a single die, there was something else that he did. It was like so similar. And he got a completely different number than I did.
Okay,
So I'm
let's
kind of worried.
yeah, so let's look at it together. Whenever it's one of these at least problems, you first ask yourself, you say, well, it's 1 minus the probability of no 3s in 4 rolls.
Mhm.
Okay, so we gotta kind of break this up and first figure out, well, what is the probability of getting no 3s in a single roll?
Okay.
So if you roll a die, normal 6-sided die, okay. And by the way, sometimes tests, they give you like a 7-sided die or an 8-sided die, so just everything changes a little bit.
Yeah.
So there's 5 numbers that are not 3.
Mhm.
All right, but since you're doing it 4 times, that's where the 4 comes in.
Right.
And then the 1 minus is the none, so that gives you the at least.
Mhm.
Does that appear to be what you did here? Yeah, it does,
Yes.
because you did the 0.83. I recommend not rounding until the end.
That
I would
makes
put all this in your calculator,
okay.
because when you're going out 4 times, when you're multiplying something 4 times, missing some of those decimals will make a difference.
Okay.
Um, what else should we do here?
Okay. Number 7 on page 4. This one, I don't know if I did it right because so it's based on an insurance company, and they're like, so how much do they make per thing, if even with these odds? And so I did it, and they make a negative 100 by what I did. And I don't know if that's really a possibility.
Yeah, I mean,
So,
you wouldn't make money if you did that very often. So
no, I don't
uh,
know if they're just trying to trick us or not, because sometimes school likes to do that, but
right.
I was just confused. I'm like, but they did it
Yeah.
all over again.
Okay. So there's a couple of paths here you have to look at. So everyone buys a policy, but they're saying that for and so okay, sorry, back up here. We're looking at from the perspective of the insurance company.
Okay.
So the insurance company gains 500, but then they lose 10,000. Okay.
Mhm.
But when does that happen? It happens 1 in 100 times.
Okay. Yes.
Okay. The second situation is that they gain 500 because there's a policy, but they lose $20,000. And this happens 1 in
No, the first one's 50. First one's
okay,
50.
sorry, yeah, 50.
I was like, maybe that's where I went wrong. I
No,
did the wrong numbers underneath the
yeah.
fractions.
And then they do this for they gain 500, but they lose $50,000. And this happens 1 in 250 times. Okay. So
Mhm.
this is like the case when they lose the money.
Right.
But it is also the case that they gain the money. They get the 500, and 49 out of 50 times they get to keep it. Do you follow that? The 1 out of 50
Yeah,
they
no,
lose
I
it,
see it. Yeah.
plus they gain the 500. That's interesting. So okay, yeah, and then this would be 99 out of 100 times. I wonder if these all add up to. Okay, let's keep going here. 500, 249 out of 250. Is this what you did in your calculation? I can't tell.
A little bit different. Okay, so the teacher did one similar. So it was, you put 500 and 500 is in plus because you don't have a minus. And then you minus 200 and then you minus 200. Okay, wait a minute. How did I get to that? Right. So you get 500 and there's 100% chance that the company is going to keep it. So you divide 500 by 100, which is 500. And you minus, then you go to 10,000 and you divide that by 50 because there's 50 a chance, 50 and 1% chance that they'd miss it. That's 200. And then you go to 20,000 and you divide it by 100. And that's 200. And then you go 50,000 divided by 250, which is 200. And then, so you go 500 minus 200 minus 200 minus 200 equals negative 100. Well, I'm not saying that's the right way to do it. That's just a way that he did a problem very similar to it.
Yeah, and what I'm suggesting here is you want to go through the possibilities. And I didn't make a tree, but the possibilities are the person makes a claim, that's the probability of that, or they don't, the insurance company just gets the money from the insurance holder. I'm going to get some numbers here for you to answer. So give me just a moment here.
Yeah.
All right, I've got this almost done here. Okay, so here, let me see if I can just snip this in. So these are the 6 cases that we just mentioned here. So the idea is that, so we're gonna make this bigger. I guess not. Okay. So the first case is this 500 minus 10,000. The insurance company ends up paying out 9,500 2% of the time. So that's 190 on average,
Okay.
because that's the product of these two numbers.
Mhm.
And then similarly, the next one is they have to pay out 19,500, and that is 1% of the time. And then the third one here is where they pay out the 49,500 because they keep the 500, and that happens 0.4% of the time. And then the other percentage of the time, they just get the money.
Okay.
All right. So the answer is the sum of each of these columns here, and then you add them together, kind of the loss case and then the non-loss case.
Okay.
So that is where you're off here. So this is minus 583, and this is 1483. So in general, they expect to make $900.
Okay.
But this is written really, I guess I would still ask, because it's really like it's dependent on. You see, I don't like the fact that these don't all add up to. See, all of these add up to 1, and what it's not clear to me is like whether the 1 out of 50 really means out of 250 it's 5 out of 250.
Okay.
And then this is 2.5 out of 250, and then you're supposed to like it's really that they get $500, the 8.5, 241.5 out of 250. I think there's something amiss here.
Okay.
It's kind of that there's too many. Yeah. It's like we could say this per policy, like, so like per policy, you get 300, 300 and 300 per policy.
Mhm.
And that's going the minus 190 and the positive 490. So the instructor wrote this question or took it from somewhere where the person who wrote it knows what the intent was, and I'm not gonna be able to give you much more information than that.
Okay, I get it.
But you were wise to notice that they wouldn't lose money. Like, you don't go into business to lose money, so it would be unreasonable for them to have a loss each time.
Yeah, no, they have to win some kind of money or else they
Yeah.
would get out of the business.
That's right.
Or charge more. I don't know, whichever one works.
Yeah. Okay, so we got a little bit of time here. What else can I answer for you? What other questions do you have?
I'm looking over. Can we do page 3, letter C, the one at the bottom of the page? I realize there's 3 C's.
Say that one more time. Page 3, letter C.
Letter C, but the one on the bottom of the page. On page 3, there's. My teacher didn't do this very well. Under the 4.
Okay.
So
meeting at least one person with the flu and 10 random encounters. That one.
Yeah.
Okay.
I think I did this one correct. I'm not really sure.
So with just like the other at least ones, you're going to do the probability of none.
Okay.
First. So it's 1 minus the probability of none with the flu. So, but it's in 10. So that comes later. So that means, again, this isn't really great. If it should say the probability that the person has the flu is 4%.
Right.
So the probability of the flu is 4%, and then 10 people would be to the power of 10.
Okay.
And then you would do 1 minus that. Now I see you did 0.96. Oh, so I'm sorry. Probably meaning at least one person with the flu, no flu. Sorry. So this is not 0.04, it's 0.96.
Okay.
Because they do not have the flu. If you'd done 0.04, you would have gotten such a small numbers, it wouldn't have made any sense at all. Yeah. And this is the level of work that I think that you need. I'm not sure, like, you have a lot of the calculations there. They're looking for the steps. They just don't want you to give a number as your final answer.
Okay.
You're doing this. So what I was attempting to do here, this will be I guess our final thought here. I was just trying to show you the sample space for a dice roll. This is the other one you see all the time. And sometimes it's easier if the image is like that list, or like this, but just keep that in mind when you're working on your problem sets here. So